find the limit if it exists. And here we're looking at the limit as x approaches negative infinity of the rational function x to the fifth minus 3x squared plus 1 all over x cubed plus 2x minus 1. Again, we are going to follow our trick of dividing the numerator and the denominator by the highest power of x in the denominator, which in this case is x cubed. So when we do that, x to the fifth over x cubed is x squared, minus 3x squared over x cubed is the same as 3 over x, and then plus 1 over x cubed. And then in the denominator, when we divide by x cubed, we end up with 1 plus 2 over x squared minus 1 over x cubed. And at this point, you know the drill. The limit of a quotient is equal to the quotient of the limits. So we can split this limit in the top and bottom. And then the limits of sums and differences are the sums and differences of the limits. So we can evaluate each of those limits term by term. And we end up with the limit as x approaches negative infinity of x squared minus the limit as x approaches negative infinity of 3 over x plus the limit as x approaches negative infinity of 1 over x squared. And then that's all over the limit as x approaches negative infinity of 1, and then plus the limit as x approaches negative infinity of 2 over x squared, and then minus the limit as x approaches infinity of 1 over x cubed. And a lot of these are pretty easy to evaluate. In the denominator, the limit of a constant is just that constant. So we've got 1, and then the other ones are going to end up being 0. Even though this is the limit as x approaches negative infinity instead of positive infinity, these are functions that are defined as x approaches negative infinity. We don't have any square roots of negatives, so those are all good. All of these are going to be zeros, except for this thing right here, the limit of x squared as x approaches infinity. And so I'm going to actually leave that like it is for now. So I'm going to keep this, the limit as x approaches infinity of x, or negative infinity of x squared. And so we know that when we take this and subtract and add 0, those cancel, and we divide by 1, and anything divided by 1 is itself. So this is going to be equal to the limit as x approaches negative infinity of x squared. And we know what happens to x squared as x approaches negative infinity. You've seen the graph of x squared. You know that it is an upward opening parabola. And so as x approaches negative infinity, x squared is approaching positive infinity. It's going up, up, and away. And so this limit is actually going to be positive infinity. And the reason for that is because the numerator has a larger degree than the denominator. That means the numerator is growing faster than the denominator, and that's why we had an infinite limit here. If it had just been x instead of x squared, that would have actually been a linear function, and the limit would have been negative infinity. Same if this was x cubed in the end. So it didn't have to be positive infinity, it could be negative infinity. But when the numerator has a higher degree than the denominator like that, you're generally going to end up with a limit that is infinite because the numerator is growing faster than the denominator. So we've got fractions that are growing bigger and bigger and bigger, either in the positive direction or the negative direction.